Hey, hello there, welcome to CS School channel. In this video we are going to look at different bits sum problem. The link of this problem is in the description of this video, so do check it out and try to solve it on your own. If you can solve it, come back to this video. So let's look at the problem statement, which is also given on the screen. Given an array A of n positive integers, we need to find the sum of bitwise differences of all the pairs in the array. Okay, so let's look at some sample inputs and outputs so that you will get the idea about the problem. Now let's focus on the first sample input, which is given here. Okay, so we are given an array with 3 elements, 1, 3 and 5. Now let's look at how many number of pairs that we can make in this array. We can make the first pair 1 1, right? So this is the first pair. We can make the second pair of numbers, which is 1 3, right? So this is 1 3. We can make the third pair as 1 5, right? So this is 1 5. We can now start with 3 and start making pairs with this 3, right? So we can make the first pair as 3 1. So this is 3 1. The second pair will be 3 3. Okay, this is 3 3, and the third pair can be 3 5. Okay, 3 5. Again, we will start with 5 and we will make the first pair, which is 5 1. Okay, 5 3 shown here and 5 5. Okay, now after making pairs, we need to count the bit differences between each of the pair. Okay, now let's represent this pair in its binary representation. Okay, so 1 will be represented as something like 1 in binary, right? And the second one will be represented as same in the binary. Okay, so if you find the bit differences, as there are only one bit and they are similar, the bit difference is 0. Okay, so that's what we have written here. Actually 0 is the bit difference between f of 1 comma 1. Now let's look at the second pair, which is this 1 3. Okay, so what is the binary representation of 1? Okay, I will write it something like this: 0 0 1. Okay, so this is the binary representation of 1. Okay, what is the binary representation of 3? It will be 0 1 and 1, right? So now let's count the number of differences in the bits. Okay, so this one is matching with this one, right? So there is no bit difference. Here we have 0, but here we have 1, so there is 1 bit difference in between them, right? Here we have 0 and here we are 0, so only 1 bit is actually differing in these two numbers, right? So the bit difference is 1 in total, right? And that's what we have written here. The bit difference between 1 and 3 is 1. Okay, now let's look at 1 and 5. Okay, so 1 has a binary representation as 0 0 1, right? And 5 has a binary representation of 1 0 0 1, right? So this is the representation of 5. Okay, let's add 0 here so that we have matching number of bits. Okay, now how many places the bits differentiate between these two numbers? So see, this place we have equal bits, this place we have equal bits, this place we have equal bit, this place we have 0 and 1. So the bit is differentiating at this place, right? So we can consider the bit difference between 1 and 5 as 1, right? And that's what we have written here as well. Okay, the bit difference between 1 and 5 is 1. Now let's look at some interesting example. Let's consider this 5 and 3. Okay, 5 will have a bit representation as 1 0 0 1. Okay, and 3 will have bit representation as 0 0 1 1. Okay, now let's count the number of bit differences. So see, these two numbers are matching, so here is no bit difference. This is not matching, so we got first bit difference. These two are matching and these two are not matching, so we got second bit difference. So f of 5 and 3, the bit difference between 5 and 3 will be 2, and that's what we have written here. Okay, so if you calculate all the bit differences and if you sum them, we get the total bit difference as 8. So hope you are clear with the first sample input. Okay, now similar thing we can do with the second sample input. We can calculate all the pairs. In this case we have pair 2 2 2 3 3 2 and 3 3, right? If you calculate the bit difference between 2 2, it's 0. If you calculate the bit difference between 2 and 3, it's 1. Again, 3 and 2 will have similar bit difference as 2 3 because numbers are similar and they will differentiate at the similar places, right? So 3 2 will have 1 only. Okay, 3 3 will also have 0. Okay, and if you sum them up, we get 2 as a total bit difference between all the pairs of numbers in this array. Okay, so that's what we need to find in this problem. Okay, so hope you are clear with the problem as well as sample inputs and outputs. Now let's look at the brute force approach for solving this problem. So this is the brute force approach for solving this problem. This approach is similar to the way in which we have just found out the bit differences in sample inputs and outputs. Okay, so what we do, we run 2 for loops. So these 2 for loops are responsible for finding out the 2 values in which we need to find the bit differences. Okay, and we have initialized 2 variables. The first one is the response, which is the final response that we need to return at the end of the function, and the second variable that we have defined is called as count. This variable will just return the count of bit differences between each of the pair. So in the for loop we have performed XOR operation. Okay, so what does this XOR operation do? Well, it does something like this. Well, let's say we have 2 numbers 1 and 3, right? The binary representation of 1 is 0 0 1, right? And the binary representation of 3 will be 0 1 and 1. Okay, what does the XOR operation does? Well, if the 2 bits are similar, it will set them to 0. Okay, and if the 2 numbers are differing, it will set them to 1. Okay, in this case 0 is not matching with 1, so the bit will be set to 1. 0 is matching with 0, so bit will be set to 0. If there was a case, if this bit was 1 and this bit was 0, it would have set to 1. So XOR operation does that only. It will write 1 if the 2 bits are not matching with one another. Okay, so after performing this XOR operation, we need to just find out how many bits are set in the final value, right? So in this case only 1 bit is set, so the bit difference between 1 and 3 is only 1, right? So that's what we need to find. That's why I have written this function get active bits, where we will pass the value and we will get the number of active bits. That means the number of ones which are there in the final result. In this case there is only 1, and that we will store in the count, and we will just add this count in the result. So I will tell you how to write this function in future. At the end we will just return this response, and that will be our final answer. Now what is the time complexity of this approach? Well, we are running 2 for loop over the array, so naturally the time complexity becomes O of n square. Okay, and as we are not using any extra space, that space complexity becomes O of 1. Okay, hope you are clear with this brute force approach. Now let's look at an efficient approach for solving this problem. So consider we are given an array with the numbers as 1 3 5. Okay, so I have listed them down here, and I have given name to the each elements of the array. Okay, so 1 is called as a1, 3 is called as a2, and 5 is called as a3. Okay, I have also listed down the binary representation of each of this number. Okay, so 1 has a binary representation of 0 0 1, 3 has a binary representation of 0 1 0, and 5 has a binary representation of 1 0 1. Okay, now let's consider the last bit of each of this number. Okay, so this row. Okay, so which number has 1 in their last bit? It will be a1 comma a3. Okay, so a1 as well as a3 has 1 in their last bit, right? Which numbers has 0 in their last bit? It will be a2. Okay, cool. So hope we are clear until this point, right? So if we consider a1 and a2, will it count in different bit sum? Yes, right, because a1 has a last bit 1 and a2 has a last bit 0. These two bits are different, right? So it will eventually count towards different bit sum, right? Because we only consider bits which are different in the final sum, right? So if we consider a3 and a2, similar thing will happen, right? As both these bits are different, we will be counting them in the final sum, right? A3 has last bit as 1 and a2 has last bit as 0. Okay, similar thing will happen with a2 and a1, because it will be just an inverted order of the same bits, right? So it will be 0 and 1, so it will eventually count towards the sum. Similar thing will happen with A2 and A3, right? If we consider the numbers from the same category like A1 and A3, they will not contribute towards the different bit sum because they have the similar last bit, right? So they will eventually not contribute towards the different bit sum. So now our question has reduced to just counting the number of pairs that we can make between these two different categories. Okay, so we can make pairs such as this: A1 A2, right? Similarly A2 A1, right? Then we can make A3 A2, right? Similarly A2 and A3, right? So these are the different pairs which we can make, which will eventually contribute to the different bit sum. Okay, so there are 4 pairs, right? So there is actually a formula by which we can do this calculation, which is the number of ways we can select from this group, which is 2, and the number of ways by which we can select from this group, which is 1, because there is one available number, right? And we just need to multiply this number, which gives us 2 into 1, right? And we need to make twice of that because we need to consider A1 A2 as well as A2 and A1, right? So we just need to do twice of this multiplication, which gives us 4 different combinations. So we can make 4 different combinations from these 2 pair subgroups. Okay, now we have just considered the last column, right? Similarly, we need to consider this column as well and this column as well. That will eventually give us the different bit sum for all the numbers in the array. Okay, so hope you are clear with the intuition. Now let's look at the actual implementation of this algorithm. So here is the efficient approach algorithm for solving this problem. Okay, so first we have this response, which will be our final response, which we will return at the end of the function. Okay, now we have run a for loop which will go from 0 to 32. Why 32? Because in C++ integers are represented by 32 bits. Okay, so that's why we are running this for loop. So if you remember, we are considering each bit separately for all the numbers, right? So we will go from the first bit and we will go till the last bit, which is the 32 bit in C++. Okay, after that we have initialized variable called as count_on. It will store the number of ones in the ith bit position for all the numbers. Okay, after that we have run a for loop which will go from 0 to size of the array. So we are considering each element in the array. Okay, after that we have just got that element into the val variable. So here is the interesting step. This will find out whether there is 1 or not in the ith bit for this element. Okay, so how does this work? I will just tell you. Suppose you just find it out and it's not equal to 0, then we are just incrementing count_on. That means we have just find out that the ith bit in this element is 1. Okay, and how to find the number of zeros? It will be just difference between size of all the elements in the array minus count_on. And after that we are just calculating how many possibilities are there for making the different sum. It will be count_on into count_of into 2, right? And at the end we are just adding that difference into the response. Okay, and at the end of this function we are returning the response. Okay, now let's look at how this particular thing works. Okay, so there are 2 operators. The first is bitwise AND. It will just do the ANDing of the bitwise. So suppose there is 1 and 0, it will do AND bitwise AND and it will return 0. If there is 1 and 1, and then it will do bitwise AND between these 2 elements and it will return 1. And there is this left insertion operator. Okay, so what it does, suppose we have this 1, right? The bitwise representation of 1 is 0 0 1, something like this, right? And we are shifting this number by ith position. Okay, so suppose I is initially 0, right? So we are not shifting that element like any times, right? So it will be 0 0 1, right, which is 1 again. Okay, now suppose this I is equal to 1. So in this case what will happen, we will left shift this entire number by 1 position. Okay, so it will become 0 1 0, right? So we have shifted this 1 to this place and we have added 1, which is default. Okay, so it has now this number has converted to 2. Okay, so what we have done here is that first we have set 1 to the ith bit position. Okay, and after that we have done an bitwise AND operation. Okay, so suppose the number is 3, its binary representation will be something like 0 1 1. Okay, so to count which bits are set, we first say, well, we will bitwise AND with 1, right? So I will be 0 and 1 left shift 0 will be 1 only. So the binary representation of 1 will be 0 0 1, right? And we will do bitwise AND, right? So both these bits are set, it will be 1, this will be 0, this will be 0. So we will get that this bit is set, the ith bit, which is 0th bit, is set. Now if we consider I is equal to 1, this number will change to 0 1 0, right? And after doing the bitwise AND, it will be 1 and 1 will be 0, this will go to 0 and this will remain 0, right? So the second position bit is also set, right? So basically this thing will find out whether the ith bit is set or not for a particular number. Okay, so hope you understand this algorithm. Now what is the time complexity of this solution? Well, we are running 2 for loops, but the first for loop goes until 32, right? And the second for loop goes till n, right? So the time complexity is 32 times n, which is equal to O of n only, right? And what's the space complexity? We are not using any extra space, so the space complexity becomes O of 1. Okay, so hope you are clear with the approach. Now let's look at the C++ implementation for the same. So here is the C++ code for solving this problem. Okay, so we need to complete this count bit function, which takes vector of integers as an input. Okay, the code is similar to the algorithm just we have seen. Here is the response, the another variable is count on. We are running a for loop till 32. In each of the iteration we are going over all the numbers in the array, and we are kind of calculating how many ones are there. Okay, and we are counting the number of zeros, we are calculating the number of differences that we can get, and we are just adding the differences in the response. Okay, the only difference is that this long integers that we have taken, because so some of this calculation, especially this multiplication, overflows, so that's why we have taken all the integers as long, and at the end we are doing this modulo operation because the problem expects us to give a response with modulo. For running this code, I have written a main function in which I have defined a vector a, and I have passed that vector to this count bit function, and I have just printed whatever results is written by this function. Okay, so now let's run this code. So we get 8 as an answer, which is also an expected answer. So hope you are clear with the problem and its solution. If you have any doubt, do ask me in the comment section. I will be more than happy to help you. We will be making more such videos in the future, so stay tuned for further updates.